guys, welcome to the second video of module number 6. So in this video we will be learning about a test named as direct shear test. But before that, let me tell you that there are many tests to measure the shear strength parameters of a soil. There is direct shear test, there is triaxial test, vane shear test, unconfined compression test. So we will be discussing each one of them. But in each test, the primary objective of ours is to find the shear strength parameters. So if you remember from the last class, we discussed the Mohr-Coulomb equation, which was tau equal to C plus sigma tan phi. So I told you that C and phi, these are collectively known as shear strength parameters. So in each test, we will be actually trying to find these two parameters. Okay. So now let us look how the direct shear test is carried out. So I have listed the steps on the left side. If you can see, the first step says that the soil is taken in a box which is split into two halves. So if you see in the right side, I have got a metallic box which is actually divided into two halves. The lower half is fixed and the upper half, it is free. So it is free to move. So to this sample, I place two perforated plates. This is the perforated plate at the bottom and this is another perforated plate at the top. So why do I place these perforated plates? So that the water that is coming out of the soil can easily drain out. Okay. The third step is I apply vertical load and horizontal or shear load to the sample. So you can see this is the vertical load or normal force applied to the sample, because of which the soil will now get compressed, right? And also I apply a horizontal load or shear force to the soil sample, because of which the upper half of the soil sample will now get displaced to the right side. The lower half will remain in its original position because it is fixed, right? Now the shear load that is being applied to the soil sample is actually measured with the help of a proving ring, which is not shown in the diagram. So here I have got a proving ring which measures the shear load applied to the soil sample. So now, knowing the loads applied to the soil sample, can I measure the normal stress and shear stress? Obviously I can. You see, I will know the normal load applied to the soil sample and I also know the cross-sectional area of the sample. So load divided by the cross-sectional area will give me normal stress. Similarly, shear force or shear load divided by the same cross-sectional area will give me shear stress. So this way I can measure the normal stress and shear stress produced in the soil sample. Now you see, because of the normal force, the soil will get compressed. So I can say that there will be some amount of vertical deformation. So this vertical deformation is measured by a dial gauge somewhere over here. And similarly, since I have applied a horizontal load to the soil sample, it will get displaced in the horizontal direction. So the horizontal deformation will be measured by a dial gauge somewhere over here. Okay. So now you see this is the direct shear test apparatus. So this is actually available in our laboratory. So you can see this blue color portion. Inside this I have actually got the metallic box which is split into two halves. The shear force is being applied through this line, okay, and this is measured with the help of the proving ring. The normal load, it is applied somewhere over here and this is being transferred through this loading mechanism into the soil. The vertical deformation occurring in the soil is measured with the help of this dial gauge, and this is actually the pump through which the instrument is operated. Alright. Now the steps which I listed earlier are actually repeated for 4 to 5 specimens. So let us try to understand what this line actually means. You see, first I take a sample which I name as sample 1, and to this sample 1 I apply vertical load and horizontal load. So obviously, because of the vertical load, normal stress will be produced, let us name as sigma 1, and a shear stress will be produced because of the horizontal load, which is tau 1, right? Now what I do, I take another new sample, that is sample 2, such that the load, the normal load that is being applied to sample 2 is higher than the normal load applied to sample 1. Okay, that means the normal stress that will be produced in sample 2 will be higher than the normal stress produced in sample 1. So I can write that sigma 2 is greater than sigma 1. And then I can say that the shear stress that is produced in sample 2, that is tau 2, will be also higher than the shear stress produced in sample 1, that is tau 1. Now why this is so? Because of the Mohr-Coulomb equation. The Mohr-Coulomb equation is tau is equal to C plus sigma tan phi, and I told you that the shear stress is actually a function or a dependent function of normal stress. So if I increase the normal stress, shear stress will also get increased, right? So this is why in sample 2, because I am increasing the normal load, the normal stress increases, and since the normal stress increases, the shear stress also increases. So this is actually repeated for sample 3 and sample 4 as well. In sample 3, I increase the load further, so sigma 3 will be higher than sigma 2, and obviously it will be higher than sigma 1. Similarly, this shear stress will be also higher than the previous two cases. And in sample 4, again I increase the normal stress, so sigma 4 will be highest of all the values, and shear stress will be also higher than all the values. So knowing all the normal and shear stress values of sample 1, 2, 3, 4, we can actually plot a graph. So in this graph, what I do, I take shear stress or tau in the y-axis and normal stress along the x-axis. Okay, so uh, this point is actually for sample 1. So I have got the normal stress, right? So this will be measured along the x-axis, and a shear stress which will be measured along y-axis, so which will actually give me the point over here. Similarly, I mark this for sample 2, sample 3 and sample 4, and I try to draw a straight line through all these points. Okay, so you will see that some points will fall in this line and some will not. Okay, so it is necessary that minimum 3 points lie along the same line. Now our aim, if you remember, was to find the shear strength parameters. That was, we need to calculate C and phi. So if I measure the slope of this line, the slope of this line will actually give me phi, or angle of internal friction. So one of the shear strength parameter is determined. Now what about C? So if I extend this line to the y-axis, okay, if I extend this line to the y-axis, I get an intercept over here. So this intercept is actually C. Okay, so you can see that I have determined the shear strength parameters C as well as phi using the direct shear test apparatus. So now we come to the disadvantages of direct shear test, but before that let me tell you that the advantage of using direct shear test is it is very quick, it is inexpensive, and as a result of which you can get very quick results. Okay, but the main points are the disadvantages. The first disadvantage is you cannot control the drainage conditions, as well as you cannot measure the pore water pressure that is developed in the soil. For example, fine grained soil, it takes a lot of time for the water to drain out because it has got a very low permeability. So this test, since it's a very quick test, hence it is not suitable for soil like fine grained soil. It is only applicable for coarse grained soil such as sand or gravel. The second disadvantage is the failure plane in the direct shear test is always assumed to be horizontal. If you look into the diagram of direct shear test, this is actually the horizontal plane of failure. It is assumed that the soil has failed by shear along this horizontal plane. But this may not be the case in all soil samples. The soil can also fail along a plane which is oblique in nature. Suppose this is the soil sample, it may also fail along a shear plane which is not horizontal, but it may be slanting. Okay, so this is the second disadvantage of direct shear test. The third disadvantage is that the normal and shear stress that we calculate are actually based on the original cross sectional area of the soil sample. But you see, uh, when the direct shear test is carried out, the upper half it will move to the right hand side and the lower half it will remain fixed. So the contact area between the upper half and the lower half is constantly changing with time, and since the contact area is changing, the shear stress and the normal stress produced in the soil sample is also changing with time. But what we do, we simply take the normal force at which the soil is failing, and we divide it with the original cross sectional area, so which is actually wrong. Similarly, what we do in shear stress, we measure the shear stress at which the soil has failed and we take the original cross sectional area, so that is again wrong. So these are the disadvantages of using direct shear test, which we will see that these are overcome by another test which is known as triaxial test, which we will discuss in our next video. So that's all for today. Thank you.